very similar to what we did for the electrical field. Okay. So here also, my sphere can be classified into two types. Okay. One day it is a hollow sphere, or I can call it as a thin shell. Okay. And then I have a solid sphere. Okay. And this hollow sphere, I can have conducting, not conducting. Similarly, solid sphere, I can have it as a conducting and non-conducting. Okay. So now we are going to look at, if I have a sphere and I have some charge in it, what will be the potential inside the sphere if it's a hollow shell, right? Or in the case of a solid sphere, inside potential, on the surface and on the outside. Okay. And very similar to the electrical field, the behavior or the expression would be very same for conducting, non-conducting, hollow shell and solid sphere. Okay. So for all these three, we will have the same expression. Okay. For the non-conducting, it will be slightly different. Clear? So we will take the first case, which is thin shell, right? Which will be both conducting and non-conducting, and solid sphere conducting. Okay. So on this color you can keep. Okay. What will happen in all the three cases is, so let's say I have a thin shell. Okay. I have a thin shell. Now I am giving some charge to it. Okay. What will happen is, whatever charge I'm giving, right, will always reside on the surface only. There will be no charge inside this. Okay. So whether it is a conducting, non-conducting thin shell or a conducting sphere, the moon case. Okay. Let me write this again. Thin shell, conducting plus non-conducting, and solid sphere conducting. In the moon case, the charge resides on the surface of the sphere. Okay. So you cannot give any charge inside. The charges will reside only on the surface. Whereas in the case of a non-conducting solid sphere, okay, in the case Lamato, you can give charges inside this. If the difference first, the charges can reside inside the surface of a non-conducting solid sphere. A solid sphere is something like your bowling ball, Mary. Okay, it is fully filled with materials, right? Non-conducting. Whereas in the case of a conducting and thin shell, where it is empty inside, charges do not reside inside. It will always reside on the surface. Is that clear?
Yes.
Yes.
So that is why we are saying that the behavior would be very similar for all the three, because the charges will reside only on the surface. Okay. We will take case by case. Okay. So the first case is, let's say I will take an outside point. Okay. The potential outside the sphere. Okay. Let's say, and the radius is capital R. My outside at a distance, small r. Okay. So where the small r is greater than capital R. So this is my condition. So what I'm going to have is like a sphere where the charges are residing on the surface. Okay. So now this radius here is R, and I'm choosing some point outside the sphere whose distance is R from here, small r. Okay. In the point, let's say this point is A. What will be the potential at A? That is what we want to find out. Okay. Now, the same case, electrical field. What will be the electrical field at point A?
KQ by R square.
in the R square.
Wow.
So the electrical field was KQ by
Small.
R squared. Patama. Now what we need to do is we need to find potential. So potential we need to relate potential and the electrical field, and we will use this expression where delta V is minus E dot dr. Sollama.
Yeah.
Right, we are going to use this expression. Appa, I need potential difference. So I need to have 2 points, right? So if I need to find the potential at point A, where should my other point be? Somewhere infinity, right? So when I say delta V, right? So delta V is nothing but, let's say, potential at point A minus potential at infinity, correct? Up potential at infinity will become 0. Up I'll get the potential at point A, which will be equal to minus integration of E dr.
Yes.
And I'm doing infinity to this point A, which is at a distance R. Clear?
Yes.
Right. So from this, I know that VA infinity will be 0. This will become 0. So I'll only have VA is equal to minus integration of infinity to R. What is the electrical field at that point? I know that it is KQ by R squared times dr. Clear?
Yes.
Now here K is constant, Q is constant. So I can take this out. So potential at point A will be minus KQ integration of dr by R squared infinity to R. Now what is integration of 1 by R squared? Previous is
R power n plus 1 by.
it will be minus 1 by R. Okay, because we're using it in so many times, right?
Yeah.
Right? And so this will become minus KQ, right? Minus 1 by R minus of 1 by infinity.
Yes.
Okay. And this becomes 0. So therefore, this will be minus into minus plus. So potential at point A is KQ by R. So how does it look like? If I have a sphere, charges residing here. Okay. From this point at a distance R outside the sphere, and let's say Q is the charge given. Up in the potential is coming out to be KQ by R. So it is similar to as if all the charges are concentrated at this point. So Lama.
Yes.
So this is equivalent to saying that I have a point charge Q at a distance of R. Potential V at let's say this point A is going to be KQ by R. Here also V at point A is coming to be KQ by R. So it appears that as if the whole charge is concentrated at the center of sphere.
So
Electrical field KQ by R squared வந்துச்சு.
ரெண்டுக்கும் வந்து charge is acting as if it is centered in the center of the concentrated in the center of the sphere. அப்ப வந்து center of charge னு ஏதாவது இருக்கா?
Center of charge.
ஆமா, center of mass மாதிரி center.
அப்படி இல்ல எதுவும் இல்ல.
Okay.
இங்க வந்து we have distributed charges அவ்வளவுதான்.
Okay.
Okay. Right. So this is the potential at outside the sphere. Now next point, the potential at surface is very similar. It will be just KQ by capital R. You can do the same expression. Either derivation that we will have this also as KQ by R. What was the electrical field at surface? Electrical field outside என்ன வந்துச்சு? KQ by R squared. Electrical field at surface KQ by capital R squared. Okay. Now the important one is the inside point. Okay, let's take the inside point. So inside point where I'm saying R is less than capital R, right? So I have all these things here. So let's say this is capital R. I'm taking some inside point, okay? In the point edukra. Now the distance is R. Now what was the electrical field inside? E inside.
Zero.
E inside is 0 because there is no charge inside. Charge it is 0. Now what is going to be the potential? What do you think? So let's do the same exercise. Delta V is equal to minus integration of E dot dr. So I need to have 2 points. Let's say this point is my, again, let's say P in which point. Okay. So I need to have Vp minus. இன்னொரு பாயிண்ட் என்ன பாயிண்ட் எடுக்கலாம்? இன்னொரு பாயிண்ட் எது?
Center.
Potential difference infinity யா?
Center.
சென்டரா? இங்க இருந்து வர மாதிரியா?
ஆமா.
சென்டர்ல வந்து 0 வா?
ஆமா.
சென்டர்ல பொட்டன்ஷியல் 0 வா? See, generally we take 2 places, right? Where one la வந்து we know it is 0. So we'll have to take an infinity in previous case la. Right? So previous case la infinity in eduthu, it is like bringing this charge from here to here. That is what we did. Now the thing here is we cannot take infinity here. Okay, in the case we cannot take infinity because what will happen here is at infinity, if I take one point at infinity, I need to do some work. I need to bring this charge from here to inside. But now I am going to have a discontinuous function because of this boundary here. In the boundary la charge I am going to have a discontinuous function. Discontinuous function இருக்கும்போது அந்த மாதிரி integrate பண்ண முடியாது நம்மளால. We can't do that work done and all. We cannot calculate. Okay. So therefore we are not going to choose the infinity here. So we need to choose a point from where we will have a continuous function, right? Or a continuous work done பண்றதுக்கு. அப்ப the other point we are going to choose is a point just inside the boundary. Okay. A point here, okay, which is very just inside the boundary. Okay. So we are taking 2 points. Okay. We are taking 2 points to find the potential difference. One is at P. The other at, we just say surface or just inside the surface. Clear?
Yeah.
Okay. Therefore, we can say Vp minus Vs is equal to minus integration of E dot dr. Okay. So let's say this surface point is S in which, okay, from S to P. Now, what is the electrical field inside the surface? We have seen that it is 0.
Yes.
Upper Vp minus Vs will be 0. So which means that Vp is going to be Vs. Upper another, what is the potential at the surface? It is Kq by R. Upper potential inside is not 0. It is Kq by R, but it is constant. You need to be very clear. It is not going to vary from the center. When I go towards the surface, it is not going to vary. It is going to be constant, but it is not 0. Is this clear?
Yes.
And E inside is 0. If I draw a graph like what we did, okay, so I have this sphere. So let's say this is the potential versus R, V versus R. Okay. This is my inside point. Yeah. This is inside, and this is all is outside. But what is the potential inside? It is KQ by capital R.
Capital R.
Right? And then what happens? It is inversely proportional to R. Here V is inversely proportional to R. And here V is constant. And with what value? KQ by capital R. Purida.
Yes.
And this point here is this R distance. Okay. If we just try to compare with what we saw for electrical field, எப்படி இருந்துச்சு நம்ம graph? Same thing here. So here I am having my electrical field, and so this is capital R. So here it is my R. So this was the inside point. This was my outside. எப்படி இருந்துச்சு நம்ம graph?
Outside line R.
First inside la எப்படி இருந்துச்சு? Inside it was 0. இல்லையா? அப்புறம் surfaceல it become KQ by R squared. And then just like this. Are you able to recollect?
Yes.
Right? So outside la KQ by R squared. Inga surface la KQ by capital R squared. Ulla E was 0. Inga V is constant inside until the surface. Right? This is the value inside plus surface. இது வந்து KQ by small r is outside. This you need to be very clear, these two things. Any doubt? Okay. Now, so predominantly for your boards and everything, in the you will probably get only a shell, and even if they give a conducting inside. So let's talk the other case. I'm not going to do a derivation and அதெல்லாம் உங்களுக்கு இதுல கிடையாது. You just need to remember the values. For the case 2, which is a non-conducting another sphere, இல்லையா? Solid sphere. Okay. For a non-conducting solid sphere, okay, what will happen here is the outside point, right? V outside is going to be KQ by R, which is same as our shell. V surface is going to be KQ by capital R. இதுவும் same. எங்க மாறும்னா only the inside point is going to vary. Okay. So V inside இங்க வந்து it will not be constant. Okay. It is going to vary, and just write the expression. So this will be KQ by capital R 3/2 minus 1/2 R squared by capital R squared. Again, உங்களோட boards இந்த மாதிரி இதுக்கு normal paper they will not ask. This is more for if you are writing any competitive exams. இதுல வந்து this question they can ask. So it is, you don't need to know the derivation, just now what to வச்சுக்கோங்க. Okay, or we will have some graphs and all, right? So the outside point and surface point, there is no change. Inside la மட்டும் என்ன ஆச்சு? அங்க கான்ஸ்டன்ட்டா இருந்துச்சு, which was equal to the same thing as surface. But here it varies with small r. புரியுதா? Okay. Now, with this expression, right? With this expression, let's say I have V inside is going to be KQ by R 3/2 minus 1/2 R squared by R squared. Okay. What will be the potential at the center? The center la enna pannum? Small r will be 0.
Yes.
Appo what will be V inside?
3/2 KQ by R.
Or V center will be 3/2 times KQ by R.
Yeah.
And KQ by R is nothing but the surface. இதை சொல்லாமா?
Yes.
V center will be, can I write this as 1.5 times V at surface?
Yes.
Okay. So this expression konja ஞாபகம் வச்சுக்கோங்க. Clear?
Yes.
Okay. Now if I plot a similar graph. Okay. For a solid sphere, non-conducting, V versus R. Okay. So this is going to be my inside point. And this is outside. Right. So my V center, let's say this is my surface point. V center, it is somewhat 1.5 times more. Yeah. So the graph will look something like this. Prida.
Yes.
So V surface, it is KQ by, this point is KQ by capital R. Then outside point, it is KQ by R. In the starting point, V center, this is VC, V center. V center is around 1.5 times more potential. But then this potential is decreasing. It is decreasing, and KQ by R varo, then KQ by R decrease. In the moon graph, then it is easier. Clear?
Yes.
How about others?
Yes.
Okay.
Yes, sir.